Okay, let's dive into this explainer and discover how mastering structured frameworks is literally like casting algebraic spells to conquer sequence questions for maximum exam marks. Welcome to the ultimate masterclass in Cambridge Mathematics past papers. Now, whether you are tackling syllabus code 0580 or scaling up to 0606, 4024, 4037, or even 4040, the strategy we are unpacking today is going to be your absolute lifeline. Picture this. You're sitting in the exam hall, the clock is relentlessly ticking down, the invigilator is pacing up and down the aisles, and right there on the desk in front of you is a brutal past paper question. We're going to look at two typical students facing this exact high-pressure scenario. Let's call them Alex and Sam. Now, Alex is our classic overthinker. When Alex sees a sequence, he just overloads his paper with raw mathematical facts. He's scribbling numbers randomly in the margins, desperately hoping something catches the examiner's eye, but his work is completely lacking a structured, analytical approach. Sam, on the other hand, well, Sam is a rusher. Sam skips the crucial steps, totally misses the specific requirements of command words like show that or derive, and ends up losing massive, easy marks despite actually understanding the core math. If we were to look at their flawed answers side by side with an examiner's red pen marks, guys, it is an absolute bloodbath of lost potential. Both of these students are missing the magic ingredient, a structured framework. Today, right now, we are transforming those red marks into green check marks.
Our strategy today maps out a crystal clear path. First, cracking linear sequences. Second, the method of differences. Third, decoding quadratic rules. Fourth, solving cubic sequences. Fifth, the exponential ratio. And finally, calculator verification tactics.
All right, let's jump straight into section 1, cracking linear sequences. This is where we lay our foundation.
So how do you predict the future of a pattern infinitely far ahead? Imagine trying to find the 100th term of a sequence without having to agonizingly calculate the 99 numbers that come before it. This is exactly what the exam command words, find an expression for the nth term, are asking you to do. The examiner is literally daring you to predict the future. They want you to move way beyond basic primary school arithmetic and step into real algebraic modeling. This is exactly where Sam usually drops the ball. Sam will notice that a sequence goes up by 3, he'll quickly jot down +3 and just move on to the next page. And boom, the examiner's red pen comes out immediately. Why? Because Sam totally missed the command word requirement to find an expression. An expression requires algebra, not just a term-to-term rule. To fix this, we're going to use a math-tailored Peel framework. That stands for point, evidence, explanation, and link. Now, before we continue, subscribe to our YouTube channel, Ace the Exams, at acetheexams_IGCSE to excel in your Cambridge examinations. Click that subscribe button and hit the bell icon right now.
Okay, let's look at the core definition we need to kick off our Peel framework. The secret lies in discovering the nth term. Think of it as a master key that instantly unlocks the value of any position in your sequence. In formal notation, which is especially relevant if you're pushing for the extended syllabus grades, we write this as T sub n. T sub 1 is your very first term, T sub 2 is your second term, and the list goes on. This right here is the point part of our mathematical Peel framework. You absolutely must explicitly establish that you are looking for T sub n. We are shifting our mindset from a simple term-to-term rule, like saying, oh, just add 5, to a robust position-to-term rule. This type of rule links each term directly to its position number, which we represent with the letter n. By establishing this variable right out of the gate, you are signaling to the examiner, hey, I know exactly what structural framework this question demands. Let's see this in action. We're going to put 60 seconds on our imaginary visual timer for our first rewrite attempt for our student Alex. By mapping out a constant difference of +5, it becomes the multiplier of n, letting us build the precise rule, T sub n equals 5n plus 2. Let's break down exactly how we got here using our structured Peel approach. First up, the evidence. The table clearly shows the terms 7, 12, 17, 22, and 27. By physically writing out the first difference beneath them, we see a constant +5. Because this first difference is constant, we instantly identify it as a linear sequence, which always takes the form T sub n equals a times n plus b. That common difference, it's our coefficient of n, so we have 5n. Now for the explanation phase. If n equals 1, well, 5 times 1 is 5. But wait, our first term is actually 7, so we must add 2 to make the formula work perfectly. Therefore, we link it all together for our final answer, T sub n equals 5n plus 2. Look at how beautifully clean that is. The red pen marks on Alex's paper are physically transforming into green check marks right before our eyes because we are finally showing the examiner a logical, undeniable flow. Moving on to Section 2, the method of differences. This is where things get a bit more complex.
So what happens when basic linear rules fail? When the sequence refuses to play nice and grow by the exact same amount every time. That's when the method of differences steps in. It is the ultimate framework, the structured strategy absolutely necessary for extracting those deeply hidden rules. This is your magic spell for those top-tier Cambridge exam questions. Listen, top students do not guess. They do not rely on messy trial and error. They use the method of differences to systematically drill down into the sequence until they hit solid bedrock, a constant row of numbers. By formally formatting your working out into layered tables, you are providing undeniable evidence to the examiner. You are literally showing them exactly how deep this sequence goes. And speaking of going deep, stop scrolling. Subscribe to our YouTube channel, Ace the Exams, at acetheexams_IGCS to excel in your Cambridge examinations. We've helped thousands of students improve by 2 to 3 grade boundaries. Join them right now by subscribing to @acetheexams_IGCS and turn on all notifications so you never miss our weekly exam strategy sessions.
All right, Section 3, Decoding Quadratic Rules. Let's level up.
Welcome to our interactive workshop. Let's kick off with Challenge 1, the data scan. I'm putting 60 seconds on the clock. Look at this complex data table. When the first difference is no longer constant, we enter quadratic territory, requiring a completely new framework. Tn equals an squared plus bn plus c. Now, what's really fascinating about this structure is how we have to drill down. We start with the sequence terms, 0, 7, 18, 33, 52. If we find the first difference, we get 7, 11, 15, 19. Uh-oh, it's not constant. Now, our friend Sam would normally panic and just guess right here, but we are going to push deeper. The difference between 7 and 11 is 4. The difference between 11 and 15 is 4. Boom, time's up on the scan. Did you spot it? We have a constant second difference. This is our evidence. The absolute moment you hit a constant second difference, you immediately write down your point. This is a quadratic sequence. Tn equals an squared plus bn plus c. You have just secured your method marks just by identifying the structure. Now for Challenge 2 in our workshop, find the flaw. I'm going to show you the steps, and I want you to think about where students usually drop marks. The crucial point here is how substituting those differences unlocks the specific coefficients, granting us the final equation, Tn equals 2n squared plus n minus 3. Let me carefully explain the explanation phase of our Peel framework. We literally have to memorize a simple algebraic key for quadratics. The constant second difference is always equal to 2a, so 2a equals 4, which means a equals 2. The very first term of the first difference row is always equal to 3a plus b, so 3a plus b equals 7. Since we know a is 2, that's 6 plus b equals 7, so b equals 1. Finally, the very first term of the actual sequence is always a plus b plus c, so a plus b plus c equals 0. 2 plus 1 plus c equals 0, giving us c equals -3. Did you find the flaw that most students make? The flaw is messing up the memorized substitution. If you forget that the first difference is 3a plus b, the whole thing crumbles. But if you get it right, you link it all together. 2n squared plus n minus 3. Beautiful, structured, undeniable logic that examiners love. Section 4, Solving Cubic Sequences. This is for the absolute exam masters. Notice how this highly erratic sequence demands 3 complete layers of extraction before it finally surrenders a constant difference of 6 at the very bottom. Look closely at the terms, -6, -8, -6, 6, 34. The first difference is -2, 2, 12, 28, still totally chaotic. The second difference is 4, 10, 16, getting closer but still not constant. Finally, we dig into the third difference, and there it is, a constant 6. Because it took 3 full layers to find a constant, we mathematically prove it is a cubic sequence. It's like a giant archaeological dig, and you just hit the treasure. Let's look at the hardcore algebraic steps required to pull this off.
Welcome to Challenge 3, Speed Writing. You have 30 seconds to write one perfect PL paragraph based on these steps. Go! By flawlessly executing these 4 simultaneous algebraic steps, you prove to the examiner that the underlying rule is Tn equals n cubed minus 4n squared plus 3n minus 6. Let me give you the examiner commentary on why this specific working out is flawless and where students usually make a fatal error. The absolute biggest error students make is forgetting the structural formulas for each layer of a cubic sequence. Just like quadratics, cubics have a master key you must memorize. The constant third difference is always 6a, the first term of the second difference is 12a plus 2b, the first term of the first difference is 7a plus 3b plus c, and the very first term of the sequence is a plus b plus c plus d. If you mess up just one single part of these memorized formulas, the whole spell breaks. You'll get the wrong coefficients and lose almost all the marks. But by laying it out clearly, step 1 through 4, substituting backwards, you are securing maximum marks on one of the hardest question types in the paper. Time's up on the speed writing. Hopefully your paragraph looks just like this logic.
Section 5. The exponential ratio. We need to completely shift our thinking here.
What if there is no common difference at all and the numbers are just exploding in size? Unlike previous patterns built on addition, exponential sequences grow by multiplication, substituting the common difference for a common ratio. And this brilliantly illustrates the absolutely critical pivot you must make in your exam strategy. When you run your first difference check and see the numbers aren't just erratic, but they are multiplying rapidly, you must immediately switch your mental frameworks. Linear, quadratic, and cubic sequences are arithmetic in nature. They build by adding layers of differences. Exponential sequences are geometric. You aren't looking for d, the difference, you are hunting for r, the common ratio. Let's look at how this visually changes our evidence table entirely.
This brilliantly illustrates an exponential leap, where every subsequent term is simply double the last, requiring a completely different analytical lens. Look at the terms: 2, 4, 8, 16, 32. If you blindly tried the method of differences here like a robot, you'd get a first difference of 2, 4, 8, 16. The difference row is the exact same as the sequence row. That is your massive glaring red flag. Do not keep digging. Instead, look at the ratio. 2 times 2 is 4. 4 times 2 is 8. 8 times 2 is 16. The multiplier is a constant times 2. Therefore, the common ratio, r, is 2. While the course syllabus might just ask you to identify the next term in the sequence, extended students must be prepared to express this structurally, often involving formulas where n is actually up in the power, such as a times r to the power of n minus 1. It is a rapid, explosive pattern that requires instant recognition on exam day.
Finally, Section 6, Calculator Verification Tactics, the ultimate safety net.
A true exam strategist always double-checks their theoretical handwritten work against practical technology. Whether you utilize a Texas Instruments or a Casio graphic display calculator, generating the sequence digitally instantly verifies your algebraic derivations. Let's look at the side-by-side comparison. On a Casio, you are diving into the OPTN, or Options, menu, navigating over to List and selecting the Seek function. On a Texas Instruments, you hit the second button, then Stat to get into the List menu, tab over to OPS, and choose Seek. What you are doing here is essentially programming the computer to simulate the exact mathematical framework you just derived by hand. If the numbers the calculator spits out exactly match the sequence printed on your exam paper, you have 100% certainty that your nth term formula is correct. You literally walk out of the exam hall knowing for an absolute fact that you bagged those marks. There's no guessing.
By accurately plugging in your derived formula, the variable, the starting term, the ending term, and the stepped increment, you secure your answers with absolute certainty. Let's decode the specific calculator syntax right here on the screen. It reads seek, open bracket, negative 5x plus 17, comma, x, comma 1, comma 5, comma 1. This translates to the calculator as generate a sequence using the formula negative 5x plus 17. The variable is x. Start at position 1, end at position 5, go up in increments of 1. The output is 12, 7, 2, negative 3, negative 8. This perfectly matches the linear sequence we could have derived by hand. This brings us to the ultimate execution of our mathematics success blueprint. If you want to stop being an Alex or a Sam, you need to follow these 3 rules that guarantee top marks. Rule 1. Command word decoding. Know exactly what expression or nth term actually means. Rule 2. Peel framework application. Point, evidence, explanation, link, using those layered difference tables. Rule 3. Time management matrix. Derive it fast by hand and verify it digitally in seconds. Students who implement these mathematics strategies see an average improvement of 2 grade boundaries, but only if they practice consistently with our weekly videos. Here's your final reminder. Subscribe to our YouTube channel Ace the Exams at acetheexams_IGCSE to excel in your Cambridge examinations. Subscribe right now to acetheexams_IGCSE and click that bell. Don't let another exam pass you by.
It really makes you wonder, right? If these structural spells can effortlessly decode the hardest Cambridge math exams, what limits exist on the patterns you can crack next in the real world? You now possess the analytical tools to transform chaotic data into precise, beautiful formulas. Drop a comment below with your target grade for mathematics and the biggest challenge you're facing. Our team responds to every comment. Like and share this video with a study partner. Ace the Exams. Your Cambridge success starts here. Keep decoding those patterns, and I will see you in the next explainer.